starting off with the four objectives, which are describing the electronic structure and key properties of transition metals, relating crystal fields, splitting color and magnetism in coordination compound, define coordination compound, and last but not least, explain the metal-ligand bonding by using basic concepts of crystal field theory.
Hi everyone, today I'm going to briefly introduce the topic of transition metals. Transition metals are elements that have partially filled d orbitals in at least one of their oxidation states. They are also known as d-block elements, and you can find them in groups 3 to 11 of the periodic table. Even though elements like zinc, cadmium, and mercury are in d-block, they are usually not classified as transition metals because their d orbitals are already completely filled, so they don't show typical transition metals behavior. These elements are called transition metals because they sit between the highly reactive s-block elements and the less reactive p-block elements, kind of acting as a bridge between the two. Transition metals are really important because they have some unique properties. For example, they can exist in different oxidation states, form colored compounds, and create coordination complexes. Many of them also have magnetic properties and are commonly used as catalysts in chemical reactions. Because of these properties, transition metals are widely used in industry, biology, and medicine. In the next part, we'll go into more detail about the properties of transition metals, coordination compounds, colors in complexes, and their applications.
So next, I will be presenting on the properties of transition metals. There are several important properties that make transition metals unique compared to other elements. Firstly, let's look at the characteristic of transition metals. Transition metals have partially filled d orbitals, which allow them to form various oxidation states. They are generally hard, strong, and dense metals. They are also good conductor of heat and electricity, making them useful in many industrial applications. Next is colored compound. Transition metals often form compounds that are colored. This happens because electrons in the d orbitals absorb certain wavelengths of light and undergo d-d transitions. For example, we can see copper 2 sulfate is blue, while nickel 2 compounds are usually green. The color depends on the metal ion and the ligands attached to it. Another important property is magnetic properties. Transition metals may show paramagnetism due to the presence of unpaired electrons in their d orbitals. Some transition metals such as iron, cobalt, and nickel are ferromagnetic, meaning they can be permanently magnetized. Transition metals generally have high melting and boiling point. This is because of strong metallic bonding involving both s and d electrons. However, there are exceptions such as mercury, which is liquid at room temperature. Lastly, transition metals show catalytic properties. They are good catalysts because they can change oxidation states and provide a surface for chemical reactions. For example, iron is used as catalyst in the Haber process, while vanadium oxide is used in the contact process. Overall, transition metals have unique properties such as distinct characteristic, colored compound, magnetic behavior, high melting and boiling point, and catalytic activities. These properties make transition metals very important in chemistry and industry.
Next, we move to the coordination compounds. As we all know, there are three types of ligands. First, monodentate that donate one pair of electrons. For example, NH3 and H2O compound. Second, we have bidentate. It donates two pairs of electrons like ethylene diamine. And the third one, we have polydentate. It donates more than two pairs like eta. Other than that, the formation of complex ions are formed when ligands donate electron pairs to transition metal ions, forming coordinate covalent bonds. For example, copper 2+ react with 4 ammonia molecules to form a complex ion. Now, we will talk about its coordination numbers and geometry. The The coordination number is the number of ligands to an atom bonded to the central metal ion. For example, hexa-aqua ion 2 has 6 coordination number and the geometry of this complex ion is octahedral. Next, there are 3 rules in naming coordination compounds. First, we have to name the ligand first, then name the metal ion. Second rule is we are required to use prefixes such as di, tri, or tetra to indicate the number of ligands. Last but not least, for anionic complexes, we have to add ate to the metal name. For example, this compound's name is tetraamine copper 2 sulfate.
Moving to colors in complexes. In order to understand the color, we have to look at crystal field theory. In an isolated transition metal atom, all 5 d orbitals have the same energy. However, when ligands approach the metal to form a complex, they create an electric field that repels the electrons in the d orbitals. This repulsion causes the d orbitals to split into different energy levels. In an octahedral complex, they split into 2 higher energy orbitals and 3 lower energy orbitals. The gap between these levels is called the crystal field splitting energy. The color we see is a result of D to D transitions. When white light hits the complex, an electron in the lower energy d orbital absorbs the specific photons of light to jump to a higher energy d orbital. The energy of the absorbed photon must exactly match the splitting energy. We can express that using this equation. The color we perceive is the complementary color of the light that was absorbed. For example, if the complex absorbed yellow light, it will appear violet to our eyes. Not all ligands are created equal. Some ligands cause a large split in d orbitals, while others cause a small split. This is known as ligand field strength. We rank this in spectrochemical series. Weak field ligands like iodide ion or chloride ion create a small energy resulting in the absorption of lower energy with longer wavelength light, like red. Strong field ligands like cyanide ion or carbonate ion create a large energy, absorbing high energy with shorter wavelength light, like violet or UV. Let's look at some real-world examples. In the copper complex, the water ligands create a specific splitting that lead to the absorption of orange-red light, leaving us with the characteristic blue color we see in copper sulfate solutions. In summary, copper 2 ion with H2O ligands creates small splitting and absorbs red light, and seen as light blue color, while copper 2 ion with NH3 ligands create large splitting and absorbs yellow or orange light and seen as dark blue color.
Next, I will be talking about the applications of transition metals complexes in biology, medicine, as well as in pigments and dyes. In biology, the iron 2 complex in hemoglobin transports oxygen in the blood, while the magnesium complex in chlorophyll is essential for the process of photosynthesis in plants. In addition, zinc enzyme complexes act as catalysts in many biological reactions in the human body. In the field of medicine, transition metals complexes are widely used for healthcare and treatment purposes. The platinum complex cisplatin is used as an anti-cancer drug to treat cancer patients. Silver complexes are used as antibacterial agents in wood dressings to prevent infection. Furthermore, cobalt-60 complexes are used in radiotherapy for cancer treatment.
Moving to the discussion, transition metals are d-block elements with incomplete d subshells, leading to unique properties like variable oxidation states and colored compounds from D to D transition. They act as catalysts by forming temporary bonds that lower activation energy, for example, ferrum in Haber process and nickel in hydrogenation. They have high melting points due to strong metallic bond and may be paramagnetic from unpaired d electrons. Coordination compounds involve a central metal ion bonded to ligands, with shapes depending on coordination number. These are important in biology, industry, and medicine.
In summary, transition metals are a unique and essential group of elements defined by their partially filled d subshells, which grant them distinctive physical and chemical properties, such as high melting points, variable oxidation states, and remarkable catalytic abilities. The study of coordination compounds characterized by complex ion formed through the interaction of diverse ligands and central metal atoms reveals the intricate relationship between coordination number and molecular geometry. Furthermore, the vibrant colors and magnetic behavior of these complexes are fundamentally explained by ligand field strength and electronic transitions. From their vital roles in biological systems and medicinal chemistry to their industrial use in pigments and catalysis, transitions metal prove to be indispensable across multiple scientific disciplines.